Okay, we're continuing with the curve sketching series of videos. This is the 7th curve sketching video, and in this video we're going to sketch this function here. All right, step 1, the domain. What is the domain here? What x's are we allowed to input? Well, okay, the only potential domain issues would come from this x to the 1/3. This means the cube root of x. And we know that for an odd root, you can input any x from negative infinity to infinity. Even roots, you can't have a negative input, but odd roots, it doesn't matter. So the domain here is you could put any x, all real numbers. Now the range, let's wait till the end and we'll inspect the graph and see what the range is. Okay, intercepts. What are the y-intercepts? Set x equal to 0. Solve for y. Okay, so the origin is an intercept. It's going to be an x and a y-intercept. The origin is the only y-intercept. Okay, what about the x-intercepts? Set y equal to 0 and solve for x. Let's just go ahead and put this into our calculator. So we've got x minus 3 times x to the 1/3. Okay, that's the main equation, so we'll set that as e. All right, so now let's solve for when e is equal to 0 for x. So x is equal to minus 3 root 3, 0, and 3 root 3. So x is equal to plus or minus 3 root 3, and x is equal to 0. Okay, now let's plot these intercepts. And so the graph, to get a good look at the graph, we're going to have the axes here go from 6 to minus 6 on the y-axis and the x-axis. So each tick mark is going to be 0.6. Okay, now the origin graph will go through the origin, and then it will go through plus and minus 3 root 3. So 3 root 3 is what? 5.2. Okay, so, all right, 6 minus 0.6 is 5.4, so somewhere around here, okay? That's plus and minus 3 root 3. That's the x-intercepts. There's 3 x-intercepts, there's 1 y-intercept. All right, now let's test for symmetry. Is this an even function? We see if y of minus x is equal to y of x. Okay, so to do that, let's come here, and then we say, okay, we put a minus sign there, and then we put a minus sign there. Well, okay, that's not gonna, okay, let's just do this. All right, minus x minus 3 times minus x to the 1/3. So what we get is minus x plus 3x to the 1/3. And this is not equal to y of x, okay? What about an odd function? So minus y of x is equal to what? So if we just multiply this by minus 1, we get minus x plus 3x to the 1/3. And that is equal to this. That is equal to y of minus x. So this is an odd function. And what that means is that every single point on the graph, so let's just, if we pick any point that's on this graph, x, y, assuming that point's on the graph, then for any point, then the point minus x minus y will also be on the graph. This is symmetry about the origin. That's what this an odd function means. Okay, now what about periodicity? Is there a number p such that if you do y of x plus p, you get y of x? So you think about like a sine function. If you shift this by this amount, you get the same function again. Well, okay, there's not going to be any periodicity with something unless there's only certain functions that we know of that have periodicity, like trigonometric functions, for example, and inverse trig functions and hyperbolic functions. So unless you have a special kind of function, I mean, there's all kinds of different kinds of functions, but unless you're dealing with some unique, type of like step function or something like that, then you'll have to go manually check and see if it's periodic. And again, you're just using this test. If you have a function like this, that's periodic. So you have to find out what the p is. But and for this series of videos, we're only sketching curves that are the main types of curves that we deal with in algebra and trigonometry. And we know that in that case, the only types that are periodic are trig functions, inverse trig functions, and hyperbolic functions. So there's no, not periodic. Okay, now let's check the endpoint behavior. What that means is we take the limit as x goes to each of the endpoints of the domain. In that case, this is minus infinity and infinity. So what is the limit as x approaches negative infinity of x minus 3x to the 1/3? All right, so what we get here is negative infinity minus 3 times, what is negative infinity to the 1/3? So that, okay, like let's say, what is the cube root of minus 8? That's minus 2, right? So a cube root of any negative number is going to be another negative number. So the cube root of negative infinity is going to be negative infinity. All right, what is 3 times negative infinity? Negative infinity. All right, so negative infinity minus negative infinity minus negative infinity. So this would be plus infinity. And so infinity minus infinity is indeterminate. So what we're going to do is, this isn't a lesson on limits. This video isn't about limits. So let's just come here and say the limit as x approaches negative infinity of e is equal to negative infinity. Okay? All right, now the limit as x approaches infinity of x minus 3x to the 1/3 is equal to infinity. So there you go. There's the endpoint behavior. All right. Next, let's do critical points, okay? So starting with the first derivative. Okay. So we want to take the derivative of the function. Okay. Now we see that x is equal to 0. The derivative doesn't exist. And so that's going to be, x is equal to 0 is within the domain. It's not an endpoint. So that's going to be a critical point. Now, let's solve for where this is equal to 0 for x. X is equal to 1 and minus 1. Okay. So what are these points? When x is equal to 0, y is equal to 0. When x is equal to 1, y is equal to 1 minus 3. So minus 2. When x is equal to minus 1, we get minus 1 minus 3x. So 3 times minus 1 to the 1/3. Cube root of minus 1 is minus 1. So minus 1 plus 3, so it's positive 2. Well, actually, I could have figured that out because this is, again, this is an odd function. And so we know that for any given point, if we know 1 minus 2 is on the graph, then you multiply each of these by minus 1. So that means minus 1, 2 is on the graph, right? This concept. So I could have figured that out from that standpoint. Okay, the second derivative, critical points are, okay. Second derivative, okay, so x is equal to 0 is 1. Now, let's solve where this is equal to 0 for x. That's it. That's the only, x is equal to 0 is the only critical point with respect to the second derivative. Okay, let's plot these points. So we've already plotted 0, 0. What about 1, minus 2, and minus 1, 2? So, okay, 1.6, 1.2, so about right in here. And then minus 2, 0.6, 1.2, 1.8, minus 2-ish. Okay. And then it's an odd function, so you just go in the opposite. It's, you're going to go minus 1, so 0.6, 1.2, oh no, 0.6, 1.2, so about in here, and then 0.6, 1.2, 1.8, 2.0, about there. All right. Okay, next step is vertical asymptotes or slant asymptotes. And typically, you don't know what the function is, and so you could imagine you have these critical points, and you take the limit as x approaches each of these x values from the left and the right, and just see what you get. If you have one of those limits goes to infinity, then you have a vertical asymptote. But even if it doesn't go to infinity, it's still part of analyzing the graph. You could take the limit as x approaches each of the critical points from the left and the right of the first derivative and of the second derivative, just to see how the slope is and the concavity is coming into the critical points. But that's not the way it's taught in typical calculus classes. You don't do curve sketching that way. That's a way you could analyze a graph in general, just from if you want to analyze it in great detail. But for curve sketching, in calculus, what you learn in calculus courses, they don't do it like that. They just say, okay, do we have a function for all the typical types of functions that we deal with in algebra and trigonometry? Is this one that would have a vertical asymptote? And the answer is no. Vertical asymptotes come into play for dividing by 0 situations, or certain trig functions, or for endpoint behavior like the endpoint of a logarithm. The starting point of a logarithm is a vertical asymptote. Like the limit as x approaches 0 from the right of the log of x is negative infinity. But that's the only time vertical asymptotes come into play when it comes to typical functions that we deal with in all of the functions that we deal with, like, in algebra and trigonometry that you learn in those courses. Now, what I would say to do, even if, for just doing a regular calculus curve sketching problem, is that if you have a critical point with respect to the first or second derivative that is associated with the first or second derivative not existing, then go ahead and take the limit as x approaches that point from the left and the right. I would say to go ahead and do that. Okay, so let's take that. That was 0 in this case. The first and second derivative didn't exist at x is equal to 0. So let's do this. Let's say, what is the limit as x approaches 0 from the left of the function? All right, so we take the limit of the function with respect to x it's approaching 0 from, and we'll do positive 1 here. Okay, this is equal to 0. Well, okay, no, that's not what I want to do. So let's do this. Okay. Let's get the first derivative. Okay, and store this as d. Okay, now let's get the second derivative and store that as, we'll call it c for concavity. Okay, so now we want to do this so this is equal to 0. Okay, this is from the right. Okay, now what is the limit as x approaches 0 from the right of y prime? So the limit of equation E with respect to x approaching 0 from the right. No. This was, but of the derivative of d. Negative infinity. Okay. What is the limit as x approaches 0 from the left of y prime? Negative infinity. So that's telling us that this critical point here is associated with a vertical slope. Okay, you see that? The limit as x approaches 0 from the, we could do this from the left and the right of just the function. This is also going to be 0 as a direct plug-in. So, because the limit as x approaches 0 in general of the function is equal to 0. Okay, so it's not a vertical asymptote, but when we check, but it still doesn't exist here. The first derivative doesn't exist here. So it cannot exist because it's a vertical asymptote, but that's not the case because of this. Otherwise, if it was a vertical asymptote, these would go to infinity. One or both of these would go to infinity, some kind of infinity. So we investigate further and we see, okay, let's take the limit as x approaches 0 from the left and the right of the first derivative. And both of those are going to negative infinity, so the limit as x approaches 0 in general of the first derivative is negative infinity. And so that's telling us that it's a vertical slope. It becomes vertical like that in some way. That's why the first derivative doesn't exist there. Let's check concavity. Let's just go in general of undefined. So now let's check from the right. Okay, so the limit, if we do the limit as x, or from the left, as x approaches 0 from the left of y double prime is equal to negative infinity, and the limit as x approaches 0 from the right of y double prime is equal to what? Positive infinity. Okay, so this is useful information when it comes to this critical point that's associated with the first and second derivative not existing. Okay, let's get increasing, decreasing intervals and intervals of concavity. So increasing, decreasing intervals. The first derivative can change signs at the critical points. So, okay. So all we need to do is plug in any number, any x within this region into the first derivative, and we know that in this entire region the first derivative must be that exact same sign. It can only change across a critical point. All right. So the first derivative with x is equal to minus 2. Okay, well, what is this? This positive or negative? This is positive, so increasing. Okay. What about minus 0.5? Okay, so decreasing here. What about positive 0.5? So decreasing here, and then increasing here. Okay, now let's check the second derivative. Intervals, or the intervals of concavity. So there's only one point where the second derivative can change signs. All right. So, okay. C with x is equal to -1. So here it's concave down. And then here it's concave up. All right. Okay, so local maxes and mins and inflection points. This curve is continuous everywhere, but when it comes to local maxes and mins, it doesn't have to be a point of continuity to be a local max or min. However, to apply the first derivative test like we're doing here, it has to be a point of continuity. But that's not an issue. This is continuous everywhere. So the first derivative test, we come to the, since we know it's continuous everywhere, we come to the critical points with respect to the first derivative, and we just see, does the first derivative change signs across the critical point? If it does, then you just look and see, okay, this goes from increasing to decreasing, so this is a local max. Here it goes from decreasing to decreasing, doesn't change signs, so it's not a local max or min. Here it goes from decreasing to increasing, so local min. All right? Inflection points have to occur at a point of continuity, but this function is continuous everywhere. And then it occurs at that second critical point, and if the second derivative changes signs, it's an inflection point. It does change signs here. Okay, so now let's sketch the curve. So we got at -1 and 1, we got these, a local max and a local min. So local max and a local min, where that slope is 0. Okay, now I'm assuming as, you know, past this point, we're going to be concave up all the way to infinity. Is that the case? Well, actually, we'll be concave up from 0 on, and that also makes sense. So we're going to go concave up, and then just stay concave up like that. Now, here, at x is equal to 0, we get this vertical slope. So we have to remember that as well. Okay, so like that. You see, so we want to make sure that we come in and get that vertical slope there at x is equal to 0. But the function doesn't change. Okay, the function doesn't change from increasing to decreasing. It stays decreasing all the way through this. Okay, and then from here, like that. Okay, so if we check everything out, we've got the x-intercepts are correct, 3 x-intercepts. It is an odd function, so for every point, you go mirror across the x-axis and then mirror across the y-axis, and you get back to the graph. The limit as x approaches negative infinity is negative infinity. The limit as x approaches infinity is infinity. All right. At the critical points, so the critical point x is equal to 0 with respect to the first and the second derivative. With respect to the first derivative, it's not a local max or min, and furthermore, it's a critical point where it's a vertical slope, and we do see that here. It's also a critical point with respect to the second derivative, and it's an inflection point. And so you do go from, at the origin, concave down to concave up. All right? And that's the only inflection point. And so when from to the left of 0, it's always concave down, all the way to negative infinity. To the right of 0, it's always concave up, all the way to positive infinity. All right? Now, from negative infinity all the way to x is equal to -1, we're increasing. That's correct. Then from -1 to +1, we're decreasing. That's correct. Then from +1 to infinity, we're increasing. That's correct. And so that's the graph. Now, if we come back here to the range, what is the range here? Well, we can see it's going to be -infinity to infinity, right? It might look like, well, no, it's just like from here to here. No, because it extends all the way to, think about these limits, right? As x goes to -infinity, it extends all the way to -infinity. As x goes to +infinity, it extends all the way to +infinity. And we know it starts at the origin, so the range is all real numbers.